All right, so today we're going to focus all on E of x. So let's review. Where does the number E come from? Okay, first of all, what is the number E?
781.
Wait, what is it?
Come on, people.
Something
2.7. Andrew Jackson was number
1828
1828 twice.
2.79045.
Good.
Isn't it like 2 point?
Did you say 1828 twice?
Yes.
Okay, yeah. 2.7, 1828, 1828,
Good job.
45.045. Okay.
Stop.
Where does it come from?
The area under the 1 over something function.
1 over the something function for the thing that's like that over by there for the.
It's
Yeah.
the value of x that makes the area under the log curve equal to 1.
Well said, Mason. Good. Okay. So, what we're going to do then is talk about what we're going to need to do. So we got to do that, and we're going to differentiate it, and then we're going to integrate it, and then of course, trivia question for today. Who said that quote?
Dalai Lama.
The Dalai Lama, correct? Not Gandhi.
That was.
Okay. So, aside from E being, as Mason explained, the area under the curve, or the value that x is, so that the area under the curve of 1 over x is equal to 1, it's also the inverse function of the natural log of x. So you'll recall the natural log of x came up because we couldn't integrate 1 over x, which made no sense because we could see that there was an area there, so we created this magical function, the natural log. Strangely enough, the natural log happens to be the inverse function of e to the x power. And you knew that from pre-calc when you did log work, where you converted from logarithmic form to exponential form. Remember, natural log is log base e of x. Okay, so nothing new there, right?
Right.
Okay, what can you tell me about that function?
You saw it last year.
Okay, good. You saw it last year in pre-calc. Think calculus-wise.
Strictly monotonic.
It is strictly monotonic, which I forgot over the weekend what that means.
When either it's always increasing or decreasing.
Which one is it?
Increasing.
It's always increasing. So if it's strictly monotonic, it must have an inverse, which we already know, and know its inverse is natural log of x. What's its domain? All reals.
No.
What's its range?
0 to infinity.
0 to including 0? Not including 0. Not including 0. It's asymptotic to the x-axis, correct. Gets closer and closer, never touches. It's just like every other exponential function, except it happens to have a base of e. Always passes through the point 0, 1, unless you manipulate or transform the function, but for the most part, e to the x.
Didn't we switch the range you made?
Who's talking?
Okay.
Mason.
Didn't we switch the domain?
Yeah, the domain of this is 0 to infinity, therefore its domain matches the range of the other one, 0 to infinity. The range of this is negative infinity to infinity, therefore the domain of that is negative infinity.
Okay, so you were asking
Because they're inverses of each other, yes, that switcheroo happens. Okay. Are we good? Anything else? What matter?
Almost.
Okay.
Good.
Okay.
Yeah, we're good.
Good? All right. That proves it. Put one into the other, you know, blah, 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 blah. Okay, let's get to the fun stuff. Pre-calc. I want to know what x is. What power do I raise? Sorry, what value do I put in for x so that e to that number plus 1 is equal to 7? Anybody recall how to solve these bad boys?
John Max, are you kidding me?
What did you just say?
He asked what E was.
Again, I forgot. See, I forgot not to quit. So.
What are you, a goldfish? Got like a 6-second memory?
Well, I didn't hear what you guys said. You guys were like talking to yourselves. I mean, he was talking like 1875. Like, what?
I was not.
1828.
Good Jamie.
Andrew Jackson.
That was.
Right.
So
Are you gonna
what's
be
the
like
number?
Memento? You're gonna have to get all this stuff tattooed on your body so you can remember what it is.
Okay, so what's the number?
What's a number?
What's E?
2.718281828459045.
I'm just gonna do 2.7.
3 decimal places is the AP standard. I'm so happy I'm recording this. Wow.
You need to have like a bloopers reel at the end of the year. Oh my god.
I'll just label it Max.
Yeah.
I'm not having a good
Is he the one that brought up the butter with the peanut butter?
Yes,
Okay.
yes, don't stop with that.
You don't know unless you try it.
The tough part is going to be going back and finding those particular videos. You know, you gotta listen to like 45 minutes of video to get to listen to 45 minutes of video.
Watch.
You watch it. Here,
Watch it.
whatever, regardless. How do you solve that?
Natural
Yeah,
law
there's a
goes
lot.
on.
Becky,
Natural log both sides.
take the natural log of both sides. Okay. Notice where I put the parentheses in there, that's important. Next step.
Move the exponent up front.
Beautiful. Where'd the natural log go? Let's get a little bit more detailed then. It went away. What does it equal?
Oh, it's just one.
It's 1. Good. And grading your quizzes, I realize that some of you didn't remember that the natural log of E is 1, or that the natural log of 1 is 0, right? Okay. So is everybody okay with this step?
Yes.
Good. Then what? Subtract 1. It's not rocket science. And then you can leave it like that, or you can plug it into your calculator and get 0.946. And again, 3 decimal places for AP standard. When solving problems with this, you don't want to use this number. You want to store the answer that you get when you plug it into your calculator so that it remains as accurate as possible. When the AP talks about rounding to 3 decimal places, they mean rounding the final answer, not in the process of doing a calculation. Okay, so that's pre-calc stuff. Are we good with that?
Yes.
Good. Natural log technique, taking the natural log of both sides pops up all the time. Okay, we talked about this already. It's continuous, it's increasing, also known as strictly monotonic. It's 1-to-1 with domain and range. It's concave up. The limit as you approach negative infinity is 0. The limit as you approach infinity is infinity. Great. Let's get to the fun stuff. The derivative. Do you have any idea what the derivative of e to the x is? Have we talked about how to take the derivative of something raised to the x power? We have, actually.
Oh, wait.
Logarithmic differentiation. We could go through that whole process, or you can just trust me. It's its own derivative. This is so ridiculously crazy. So we get these 2 sentences. The derivative of e to the x is e to the x. The derivative of e to the u is e to the u du dx. What rule is this down here? Chain rule, correct.
Why is it like that?
Because if u is another function, you have to chain on the derivative of that function. If it's e to the x squared, for instance, you would get itself chained on with the derivative of that exponent. Here we go.
Wait,
The second derivative?
if you have E, okay, number 1, then why don't you chain on that?
I do. What's the derivative of x?
Oh,
You got him on first life.
So if it's its own derivative, then what's the integral of e to the x?
Yes.
E to the x. It's its own integral. I think we got some examples first. Yeah, let's do an example. What is that? What's the answer?
Times 2.
Times 2.
Yeah. Sorry.
Taylor, where'd the 2 come from?
Chain rule.
Chain rule, correct. That's the only thing that's going to trip people up, is forgetting to attach the chain rule to it. This will be a little bit more funner. Some cheese with that wine.
If you bring the wine with cream cheese.
I don't like my job, why not? All right, what do you got? Good. I'll get you started. Wow, that's a weird E. Okay. Times?
Three over x squared. Why are this?
Hi.
Is that right?
The negative?
Oh, right. Yes, try sometime.
Remember when you take the derivative, you reduce the power? Only one chain. And of course, it's not going to stay that easy. We're going to get, you'll get something like, what is the derivative of e to the xy? That'll be fun. Product rule action for you in there.
Where'd you get? Can you do A? So you got like.
It's its own derivative,
Yeah.
chained on with the derivative of the exponent. Derivative of 2x minus 1 is 2.
And then it's just okay.
I moved it out in front so it doesn't get confused with anything else. Senor?
So if you have a chain rule inside the exponent, you have to add on a second derivative as well, depending on the equation.
Yes.
Right.
Yeah, it could get fairly nasty. The basic premise is there, though. It's its own derivative with the chain.
Right.
In that chain, you may have to chain. Or you may have to product rule, or a quotient rule, or a cry, or, whatever happens to come up. Okay, the screen just went blank. I don't know why. There we go. Integral, like we said, it's its own integral. What's the matter? You got a question?
Me?
Yeah.
No, she said I was talking to myself. She said I need to come on it to you, but I wasn't talking to you. But yeah.
Notice that in number 2, it's going to require a UDU problem. Okay, we good? Ready for an example?
Yeah.
Oh.
Change, I'm fine already.
What's U?
3x plus 1.
Common mistake with these problems is that people forget the UDU and you lose that constant out in front. It still has to be done as a UDU. The only one you don't have to do as a UDU is this, because that's just itself. Hockey dog. Oh wait, I think I did that. Oh yeah, okay. Wait, why did I just? Yeah, we did that. All right, day 80. There's actually a mathematical equation that will give you the bat symbol on your calculator.
What is it?
I don't know.
I saw it on Facebook. It's like super duper long.
Yeah, it's not pretty.
takes
It looks like it's
It
that
actually
many functions.
What's that?
It looks like it's
Okay, so finish up 5-3 from the weekend. You should be able to handle the derivative problems now. Do the first day of 5-4, which is day 80. We'll spend tomorrow going over all those problems. Tomorrow you'll have the second day of 5-4 for homework. And then on Wednesday, Mr. Rath will cover 5-5 with you, which is working with logs that aren't base E. And anybody have their assignment sheet handy? When's our next quiz? We got a ways, right?
It's next Tuesday.
Next Tuesday. Excellent.
Tomorrow?
Sure. No, not tomorrow. Next Tuesday.